Hi, and welcome once again as we finish talking about our unit on expressions, equations, and functions as we focus on looking at functions as they appear as a graph and how we can tell if if a graph represents a function, and also how we take a function and represent it as a graph. So let's take a look at definition of a function as a graph. So we use a graph when we represent a function, just like we use a table uh, to help represent a function. Now we're going to take a look at how we represent that on a graph. So if we know that a table represents a function, remember last time we talked about each input has exactly one output. Okay, those input and outputs form an ordered pair, and with the input being the first point, the output being the second one. Remember, the input and output are also the x and y. The other way we referred to them was the domain and range. So we can take those ordered pairs and then plot those on a graph. The horizontal axis of the graph is the input, the x, the independent variable. The vertical axis will be the y-axis, or the output, or the dependent variable. So that's how we represent functions as graphs. So let's take a look now at how we can graph the function. Once we have the rule for the function, how do we go about making a graph? So we'll kind of go through the process that we did before. Let's take this function y equals x plus 1. We know the domain has to be 1, 2, 3, 4, and 5. So first thing we want to do is create a table. The general term for that is an input-output table. It can sometimes be referred to as an XY table. But whatever the variables are will depend on what you're using. So for this input-output table, we're using the variables x and y because those are two variables in our rule. Now the domain is 1, 2, 3, 4, and 5. So in our table, we can put those values in. And like I said before, if you prefer to make this table vertically, go ahead and do that. I've just done it horizontally for you here. Now we plug those values in and evaluate. So if I put 1 into the equation, 1 plus 1 is 2. That's going to be the corresponding y coordinate. If I put the x coordinate in, 2 plus 1 is 3. 3 plus 1 is 4. Put 4 in for x, 4 plus 1 is 5. And put 5 in for x, 5 plus 1 is 6. Okay, so now we've created our table. We transfer that table onto our graph. The way we do that is we plot a point for each ordered pair. Okay, so the ordered pair orders our input and output together as a coordinate. Okay, so we take the xy. So for instance, 1, 2. So we'll go ahead and plot a point here at 1, 2, 2, 3, 3, 4, 4, 5, and 5, 6. And there's our graph that represents the function y equals x plus 1. So why don't you go ahead and try the example below with the function y equals 2x minus 1 and see if you can create the graph for that. Pause the video and check in just a moment. So as you can see, I entered my domain 1, 2, 3, 4, and 5 into the input, and I plugged those values into the function rule to create my output. Once I had those, I created ordered pairs and plotted those on my graph. Notice this point 5, 9 on my y-axis didn't quite go high enough, so I just kind of estimated. Okay, so now that we've looked at how to graph a function, let's take a look at how we can tell whether or not a graph represents a function. We did that with tables by taking a look at a mapping diagram to see if each input had exactly one output. So we can do something similar here with this first example. Well, with the 5 dots, maybe it's 6. Let's make an input-output table. Okay, and let's just see if this matches up, if each input has exactly one output. So let's take a look at the bottom point. It's over 2, down 1. So 2, -1, and then we're at 2 again, and we're at 0, 2, 1, 2, 2, 2, 3, 2, 4. Okay, so we can just quickly sketch out a table for that one. And let's try a mapping diagram. So the input 2 goes to an output of -1. These are all 2, so 2 goes to 0. It also goes to 1, goes to 2, to 3, and also to 4. So it becomes evident that for each input, we only have one input, 2. There are multiple outputs. So this would not be a function. Okay? As you can see, each input, if we put 2 in, there are multiple outputs because there are multiple points above and below. Okay? So let's take a look at the next example. We've got this U-shaped parabola. Does each input have exactly one output? So does each x have exactly one output? Each y? Looks like each time I put an x value in, there's only one spot for a y. So we'd say yes, that is a function. Okay. The next example. Does each input have exactly one output? Each time I put an x value in, do I get only one y? As I work my way along the graph, it appears that same thing, yes. That is a function. Then we take a look at the heart. Okay? As we look at that function, you look at each input. Let's try at 1. Okay? At 1, I've got maybe 4. If I go to 1, 2, 3, 4, I can be at 0, or I can be at 1, 2, 3. So it appears that I have multiple outputs for an input. So that would not work. That would not be a function. Okay, let's take a look at some more examples. Why don't you just look at these 4 and make a decision for yourself. Pause the video and then come back and I'll show you the answers. Okay, now that you've had a chance to look at it, we take a look at this funny looking graph here. We would say that it's not a function because there are times when an input, like say here, at -1, 2, 3, 1, 2, 3, 4. At -4, I've got multiple outputs. I can be up here at about 2. I can also be down here at 1, 2, 3, -4. So there are 2 times when I have multiple outputs for this input. Same here. If I have an input of 2, I can be down here at -1 or up here. So multiple outputs for an input, which makes it no longer a function because it doesn't follow a rule every time. This one, we would say yes. Each time we look along the x-axis, there's only one, and there's exactly one output. Same down here for my domain. Each input has exactly one output. And for this one as well, each input has exactly one output. So that brings us to a generalization that we can come across when we're checking a graph to see if it's a function. Some people refer to it as the vertical line test. And it's just a fancy way of saying, does each input have exactly one output? As I look along the x-axis, each input has only one output. Same here, each input has exactly one output. Here, each input has one, this one has one, but this input, this has 3 outputs, which disqualifies it from being a function anymore. So it's known as the vertical line test because if it is a function, no vertical line passes through more than one point. Every vertical line I can draw only goes through one point for a function. goes through multiple outputs, it's no longer a function. So we can apply that as we look at the graphs here. So this first one, an input of 1, has multiple outputs. So that would not be a function. Whereas the next example, as I look at the inputs, this one has 1, this one has 1 output, this one has 1 output. An input of 4 only has 1. Each x-axis, each point along the x-axis has only 1 output. So we would say that yes, that is a function. You could convert those graphs to a table and use your mapping diagram to test whether it's a function or not as well. So that wraps up everything that we're going to talk about with functions as graphs today. We know how to take a function or a function rule and plot it onto a graph by first creating a table. We know how to take a look at a graph and tell if it's a function or not. So do the practice problems now. If you have questions, as always, bring those questions to class, and we'll work through some more problems as we look at functions as graphs. We'll see you later.